Welcome back to another problem. Let's begin. So we're doing another plane kinematics of rigid bodies problem. And so given the problem statement, we have when the following mechanism rotates, the shaft is going to oscillate back and forth. So they want us to derive an expression for the velocity and acceleration of the shaft, which to do so, we will denote that as having some point S on the shaft. And so as I was saying last time, it's always incredibly helpful to physically or to mentally think about what physically is going on in the system. So you can imagine as this point P rotates with some angular velocity or acceleration, I might get at some time t a point P prime. And you can imagine what that's going to do to the system is this shaft is going to be moving in the left, and we might arrive at some point S prime. And then as it continues to rotate counterclockwise, I might have some point P double prime, and that will become point S double prime on the shaft. And with this oscillatory motion, we can perhaps derive an equation for the velocity and acceleration. And as you can probably guess from the cyclical nature of the motion, it's going to involve some kind of trigonometric function. And so with that kind of insight, we can just begin by writing down what we want to know. So we know that our velocity and acceleration of the shaft is going to be completely governed by this point P, and specifically its location with respect to point S on the shaft. And that's because of the physical constraint that pin is inside this orange structure here. And so what we can do is we can just write a simple distance relation where this point can represent S, and then this point represents P, and then we have the actual distance between two said points. And that will just be X. We'll call that distance X. And X is going to be the contribution of L, the distance from point S to, or the distance from the end of the rod to the vertical portion of the shaft, and then plus this little component called XP. And as you can probably see from the geometry of this problem, XP is just going to be equal to R cosine theta. So then that consequently makes X equal to R cosine theta plus L. Okay, so we now have a equation that's governing and or telling us where point P at is going to be relative to point S at any given time, or at any given angle. And so if we want to determine the velocity, because we know point P is constrained and that's related to the velocity or position of the shaft, if we just take a derivative of X, we will then have a relation for the velocity of S. So if we did X dot, that's going to be equal to, we have R cosine theta dot plus L dot, which is then going to be R dot cosine theta plus R times negative sine theta, theta dot with the chain rule. However, we know that this radius value here, we are assuming that the disk is constant radius, so R dot is just going to be 0, so this entire term is 0. And likewise, L dot is not going to change. This horizontal portion of the shaft is not going to shrink or expand. So that also is 0. So X dot, which we will just call S dot, which is the velocity of the shaft, is just going to be equal to minus R theta dot sine theta. And then if we want to write it in the parameters that we were given, that's just going to be minus R omega sine theta. Okay, and we can box that up. So there's part one. So now all we got to do is take the acceleration. And so all we're going to do is take our previously derived expression and just do another derivative to it to obtain the acceleration. So S double dot is just going to be equal to S dot dot which is going to be equal to minus r omega sine theta dot. Now, as you can probably see here, if you were doing what I did and didn't previously recognize that the radius is going to be constant, we have three terms that are going to vary or possibly vary with time. So whenever you're doing the product rule or chain rule with these kind of problems, I always find it helpful to use the commutative property or associative property and associate r or w in brackets so that we can just easily take time derivatives in a very succinct way. So what we can do here is we'll do minus r omega times sine theta dot plus minus r omega sine theta dot. Okay? But as we can see here, in minus r omega, that whole entire quantity with the time rate derivative, we're going to have to do the product rule again for that. So we're going to have minus r dot omega sine theta plus minus r omega dot sine theta plus minus r omega cosine theta theta dot with the chain rule. As before, this term is just going to be 0 because r dot is 0. And so that leaves us with the following expression. If we plug in for omega dot is equal to alpha, which is the angular acceleration, we will just have that s double dot is going to be equal to minus r alpha sine theta minus r omega cosine theta. Theta dot is omega, so we'll just have omega squared. And then if you just really wanted to simplify, you could pull a negative out and write that in case you don't like seeing the negatives there. And that's all we got for this problem. So to summarize, we recognized the constraint of the point P with some point S on the shaft. And due to the constrained cyclical motion of point P, we're able to derive an expression for the velocity and acceleration of the shaft. Okay, that's it for this problem. I hope this was helpful, and I hope to see you around for the next video. Thank you.